Explaining AI has been established as a requirement for trust and adoption for high-stakes domains. Interesting questions about explainable AI include what are the various ways in which explainability can be provided for black box machine learning algorithms? What is the importance of data for explainable AI? And what are the open challenges for explainable AI? Hello, everyone, and thanks for joining us. My name is El-Sharif, and I'm a steering committee member at Aggregate Intellect.
And I am Rehman Zafar, and I am also a steering committee member. Today, we are very pleased to be hosting Nadia Burkart and Marco Huber. Nadia Burkart received her bachelor's degree and master's degree in business informatics from the University of Applied Science in Karlsruhe. Since 2013, she is a research scientist at Fraunhofer Institute for Optronics System Technologies and Image Exploitation (IOSP) in Karlsruhe, in the field of decision support systems. In this context, she is currently leading various projects on explainable machine learning solutions in several domains. Besides her main project business, she is working on her PhD thesis in the field of explainable machine learning. Marco Huber received his diploma, PhD, and habilitation degrees in computer science from the Karlsruhe Institute of Technology, Germany in 2006 and 2009 and 2015 respectively. From June 2009 to May 2011, he was leading the research group Variable Image Acquisition and Processing of the Fraunhofer IOSP Karlsruhe, Germany. Subsequently, he was senior research with AGT International, Darmstadt, Germany until March 2015. From April 2015 to September 2018, he was responsible for product development and data science services of the Kotana in division at USU Software AG Karlsruhe, Germany. At the same time, he was an adjunct professor of computer science with the KIT. Since October 2018, he is a full professor at the University of Stuttgart. At the same time, he is director of the Center for Cyber Cognitive Intelligence (CCI) and of the Department for Image and Signal Processing with Fraunhofer IPA in Stuttgart, Germany. His research interests include machine learning, planning and decision making, computer vision, and robotics.
So Nadia and Marco will be presenting a survey on the explainability of supervised machine learning. They're also going to have a demo of a solution that they've implemented to the audience. Please post your questions in the chat, and we will be asking your questions immediately after the presentation. So without further ado, I will now turn over the presentation to Nadia and Marco. Please take it away.
Okay, thank you. Thank you for having us with you, and we would like to give you some insights about the survey we did over the couple of the last months. Let's start with a short motivation why explainability in the context of machine learning and artificial intelligence is so important. This one is, let's say, rather a nice fun example, but we will get a bit more serious in a second. Consider the situation that we would like to build a classifier which is classifying wolf images from husky images. I guess everybody from us knows roughly how to do that. So we present some images of the two classes and learn, for instance, a neural network. In this case, we have an image of one of these animals, and then we, of course, could ask ourselves, well, what kind of animal do we see here? I think everybody has an impression, and probably everybody would come to the conclusion that we do see a wolf here. Similarly, we have a different image, and everybody can ask himself or herself, what do we see here? And here we see a husky. So this is a relatively easy task for modern neural networks and machine learning models. And we could train a classifier on that will get some decent results, some decent accuracy. And here you see on the right-hand side some of the predictions on the top, and together with the true label of the image. And we will see that in the most cases, our machine learning model get the answer correct. It's just doing one error here. And this error, however, is quite important. since here we can see that the classifier is actually not working as intended. We can see that usually we have wolves together shown with snow in the background, and we have huskies shown with no snow in the background. But this particular image is an exception. Here we do see snow, but not together with a wolf. We see it together with a husky. And if we dig deeper into this learned model, we will come to the conclusion that we actually do not learn some characteristics of the animal. Instead, we're just building a snow classifier. So the model is training actually not what it should train. This example you will find in a nice paper by Samir Singh. And it's showing some importance why explainability is so important to get like biases or other wrong features that are used by a machine learning model to do its predictions. Of course, this is a rather fun example, but it can become quite serious if you consider this situation. This is a study done by ProPublica about a software which is called Compass, which is a crime risk assessment tool, which is used actually in the US. This tool is used to predict the risk of a person to recidivate. And the numbers you see here is the prediction of Compass. The lower the number, the lower the risk. And you can see here, for instance, by Vernon Prater, that the software was predicting a rather low risk of recidivation. But actually, later on, this guy was doing a grand theft. On the opposite, by Brishn and Borden, it was predicting a very high risk. 10 is the maximum number, by the way, so 8 is already quite high. So this software was predicting a high risk, but actually, Brisha was never recidivating again. Of course, you could say, yeah, well, I tuned it a bit and selected very specific examples, but we've probably found out that there's a severe bias in this program. You can see it also another example on the right-hand side, that for Dylan Fudgett, there was a low-risk predictor, but actually he was then conducting through drug processions, while for Bernard Parker, who get the maximum risk, he never recidivated. And here's some outline of the study done by ProPublica, and you will see that this software is actually discriminating people of color. And then, of course, having a machine learning model, and these guys who are doing the Compass software using machine learning have somehow introduced some bias in the software, and it can be, and this explains again why explainability and increasing transparency for such kind of models is so important. In this case, it's actually impacting the life of people. So what is actually our problem? We see that we have nowadays very powerful machine learning and AI system, but many of them are opaque and non-intuitive to the people. And then here comes the user who might have some questions like, why did you do this particular prediction? Why didn't you do something else? Why did you fail, as we have seen in the previous examples? And many of these questions often cannot be answered, or just can be answered if we use soft solutions from the explainable AI domain. And so we digged into the various solutions in our survey, where I would like to hand over to Nadia.
All right. So trust has several properties like fairness, responsibility, auditability, or accuracy. But explainability is one of the key enabler to trust AI. In Europe, we have the ethic guidelines for trustworthy AI, prepared by the high-level expert group on AI. This is an independent expert group which was set up by the European Commission. They work on fundamental rights and ethical principles like fairness and explainability. All right. So let us have a look at the public perception of XAI. The research in the field of explainable and interpretable machine learning is definitely exploding. There's nearly no day where no new research work is published. Also, several newspapers address the topic of explainable AI, like, for example, in the Forbes magazine. Also, explainable AI is mentioned in the Gartner hype cycle. It actually is between the stages innovation trigger and peak of inflated expectations. The time required to get to the plateau of productivity is 5 to 10 years. In contrast of doing only technical evaluations between the different approaches, there are also works that examine qualitative analysis of machine learning models and the explanations. The main findings were that the visualization of the feature importance was very helpful. Non-experts preferred simpler explanations that only explain a specific decision. Experts preferred to understand really the entire model. And also among experts and non-experts, short explanations were preferred overall. All right. So let us have a look at the taxonomy of XAI. So there are inter-hoc approaches that are divided by interpretable by nature or interpretable by design. We will describe them later. Inter-hoc approaches are always specific approaches. Post-hoc approaches can use a surrogate model, or the explanation can be directly inferred. The explanations can be either local, that means that they are for a certain instance, or they can be global for an entire model. Yes, okay. Yeah, also global explanations are sometimes called static because there is no change, and local explanations, because they are calculated for each instance, are called dynamic. Okay. So, yeah, now we are going ahead to the 5 types of XAI. First, we will start with the supervised machine learning, which is our actual problem statement. And yeah, okay, so we have the first approach, which are post-hoc explanations, and then we have interpretable models. Then we have global surrogate models. After that, we have instance explanations, and then we have the local surrogate models. Now we will dig into them. All right, but let us start to see where the journey starts. As I said, we will begin with the supervised machine learning problem. So let us have a look at it. So we have data and the model that is parameterized by theta. Most famous examples are linear predictors or neural networks. The estimation of theta is a typical optimization problem where we, for example, try to minimize the error on the training data. And the resulting model F is either a black box, which is the neural network, or a white box, which can be a linear model. All right. So let us have a look at the first XAI type. Those are called post-hoc model explanations, where we have the learning algorithm, and the learning algorithm constructs the black box, and thereby we directly infer an explanation. Okay, so we have some running examples on the IRIS data set. I think the IRIS data set doesn't really need an introduction because everyone knows it, but those who not know it, it's a multivariate data set. It is for the task of supervised classification problem. It contains 50 samples of 3 species of iris. The class labels are versicolor, Platosa, and Virginica, and it contains 4 attributes. All right. Okay, so here we have an overview of common approaches in the field of post-hoc model explanations. You can find them in our paper. So common approaches are, for example, partial dependence plots. PDPs illustrate the marginal effect of 1 or 2 features on a predicted outcome. PDPs show whether the relationship between the charges is complex or monotonic or linear. Another approach is random forest feature importance, where we measure the importance of a feature by calculating the increase in the model's prediction error after permitting the feature. the feature is important if shuffling its values increases the model error. Okay, so let us see some examples. As you can see, we have two types of PDPs over here. The PDPs are presented, as the name suggests, as plots, in which we either plot a classification against its partial dependence on one feature, as you can see on the left side, or two features against each other with a map plot, which you can see in the middle. The PDP shows the correlation of a feature that it has to the classification of a certain class. In this case, it's Virginica. The plot shows the increase in Virginica probability if the petal length is greater than 3 centimeters and the petal width is greater than 1.8 centimeters, for example. Another approach on the right side you can see is global feature importance. The global feature importance returns lists assigning an importance score to each feature. If you sum it up, you will have 1. The importance tells us, or the user, what features are considered the most by the model. So this is a pretty first good entry to have some kind of explainability, but they definitely should be combined with more explanation approaches. Okay, so let us get ahead to the second type. Those are the interpretable models. Okay, so we have, as I already said, two types in there. We have the models that are interpretable by nature. So the learning algorithm thereby is not definitely constructed to be interpretable, but as I said, it's by nature interpretable. And on the other hand, we have the interpretable by design. So thereby the learning algorithm is explicitly optimized to gain interpretability. As you can see, we have also an overview of different approaches, and we're going ahead to the examples. All right, so as you can see on the left side, there's a decision tree with a depth of 3. The nodes illustrate which feature is considered, or more precisely, which decision is made to split the data set into the branches. So the first split is at petal width 2.45 centimeters. The two last splits are either at petal length or at petal length at 4.8.5. So those examples illustrate that a decision tree with a depth of, like example 2 or 3, is still comprehensible. And on the right side, we see an example of a rule list. This was generated by the algorithm Bayesian rule lists. They construct rules that try to be accurate, but also interpretable. Okay.
Okay, so I will take over again. Let's also consider us now the remaining 3 types of explainable AI. The next type is global surrogate models, where we still have a black box model, but we, in addition, create another model, which is called a surrogate, and this is then used to create an explanation. I give an example how this can work. Consider that we do have a deep neural network as a black box, and we use a decision tree or a rule list as a surrogate, and we would gain, as mentioned before, model explanation. So we would like to have a global explanation of the deep neural network. In this case, we merely consider a classification task, but it would work similarly for regression. There's a quite naive way how this can be achieved. Here, you consider the trained neural network as some kind of a ground truth generator or an oracle. That means you generate data out of the neural network. To use these data to fit a decision tree or a rule list. And then you use this decision tree to explain the predictions of the neural network. This is a relatively simple idea, and when it's done naively, as explained, it is rather limited. which is somehow obvious. We know that the representational power of a decision tree is rather limited. We will get a low fidelity. That means that the fit of the decision tree to the network is rather low. And we also get a low accuracy because also the fit of the decision tree to the data is bad as well. So we get actually a lose-lose situation here. But this idea can be significantly be improved. And this is an idea that we are currently working on, is to use specialized regularizers in the neural network training that would allow to fit a decision tree or a rule list better to the neural network. As you all know, and also as Nadia introduced, usually machine learning problems are optimization problems. So we have usually some kind of a classification loss that we would like to minimize. And then what is also very often done is that we incorporate a regularizer term into the objective function. But so regularization is quite well-known topic in machine learning. It is usually used to get some kind of a simplified model in order to avoid overfitting. In our case, we would like to use the regularizer not only to avoid overfitting, but also to allow to get a very good fit of the decision tree or the rule list to the neural network. This idea actually was proposed by Wu at Alumni in the year 2018 with an approach which is called the tree regularizer. The approach roughly works like this. They do learn a multi-layered perceptron as common with a specialized regularizer. Then they use the predictions to train also a decision tree. And then they measure the complexity of the decision tree. As Nadia mentioned, the larger the decision tree, the less comprehensible it is for the human. So the goal is to get a decision tree which is rather short, but still accurate. And therefore, they designed a specialized regularization term. But unfortunately, this regularization term is not differentiable, so it cannot be used in a gradient-based optimization of the neural network, which is usually used, like it cannot be used directly in backpropagation. So what they did instead, they used another neural network to estimate the complexity of the decision tree. And then this estimate is used as a regularization in the neural network training. It sounds a bit complicated. It is actually a bit complicated. You have now 3 machine learning models. They somehow are interacting. If it works, it is quite good. You get very nice results. You get good decision trees that are rather short and that explain the neural network nicely, but you need to do a lot of parameter tweaking, and it's also very slow. So what we did is to go in the same direction, but find a regularizer which has the same properties, but is differentiable. And we find something which is combining sparsity, which is usually used in neural network training, together with orthogonality. So we enforce the neural network to produce decision boundaries which are axis aligned. I do have an example here. So this is an example of an axis-aligned decision boundary. And then we all do know that rule lists and also decision trees are generating decision boundaries which are also axis-aligned. So we drive or we force the neural network to take decision boundaries which are very similar to those of a decision tree. And then this would allow the decision tree to better approximate or to better fit the neural network. That this works, I would like to show you in a short demonstration. This is a toolbox that we are currently working on. We use a data set that is used in manufacturing to control the quality of steel plates. So this is a classification problem where we would like to differentiate 2 different classes of defects. So in this case, we now live train the neural network and we use our specialized regularizer. Then, of course, you could try to inspect the neural network, which is rather complicated. Now you will, of course, can dig into the network, but the numbers you get are somehow meaningless. So we use then a decision tree. Unfortunately, the marks here are in German, but this is not that important. The most important is here that you get a rather simple decision tree. So it is rather short. It just contains 3 features. And on the right-hand side in this chart, you can see that the fidelity, which means the fit of the decision tree to the neural network, is really high. It's 97%. So this decision tree can now be used to explain the predictions of the neural network. And this decision tree is then the surrogate that can be used for a closer inspection. So in this toolbox, we can now also dig deeper into the decision tree. For instance, we can generate a set of rules, which can also be ordered by the relevance. So the higher this number, the more important is this rule, because it's covering more data. You can generate visualizations like the decision boundaries and many things more. I will switch to the presentation to come to our 4th type of XAI, which is now we're entering the local explanations. This one is an instance explanation where we directly use the prediction of the black box model to generate an explanation. This is probably the most common approach to generate explainability for various kinds of machine learning models. So this list is rather low. I will just show you an example which is very popular nowadays because of, let's say, the strength of neural networks in image processing. So I will focus on the lower part of the table where we use image classification problems that are solved by means of convolutional neural networks. A very common approach is to generate some attention maps, which means we generate a heat map, which is then overlaid to the original image and highlight parts of the image that were driving the prediction of the neural networks. There are many examples to get this kind of heat maps. One of the most popular one is GradCam, but there are, of course, many others. And then, let's say, the higher the color, the more red the color is, the more important is this part of the image for the classification. The nice thing is these kind of heat maps often are not that well self-explainable. There's often a lot of, let's say, level of interpretation necessary to get the right understanding of this kind of heat map. In this example, it's also interesting to see that in the image on the lower left, the model was predicting a Tesla car, which is correct, but we can see from the heat map that its prediction is not only based on the car, but it's also based on the logo that you can see here on the background. So in this case, I think it's nicely revealing that the prediction is not only based on characteristics of the car. If this is good or bad, this maybe has then the employer, the guy who is applying this model has to decide. Let's come to the last and 5th type, and this is then the total different types of XAI models that we found so far in the literature, which is a combination of surrogate model and local explanations, which is then obviously called local surrogate model. The maybe most famous example here is the LIME algorithm, which is generating a linear model as a surrogate, but only for a very specific data instance. And then there are various, let's say, advances of this version of LIME. And another very important representative of this class is then the SHARP algorithm, which also gained significant importance in the machine learning community. But I would like to stick a bit more to the LIME because it's rather easy to explain and it is very often employed. LIME works like this. You have a data instance, which is classified by your black box machine learning algorithm. And then LIME tries to find a locally linearized model of the black box classifier. And it's doing like this, that is sampling data around the input data. Then this sample data is classified by the machine learning algorithm. And the closer the data instance is to the original input, the higher it gets a weight. And based on these weighted samples, then the algorithm is generating a linear decision boundary. And this linear model is then used to explain this data instance. And it's obvious if if you change the input data, the local model changes as well. But this local model is a surrogate of the actual black box machine learning model. We also use quite often LIME to drive explanations. This is an example that we were using in decision support systems. In this particular case, it is a boat classification or ship classification algorithm. We have 5 different kinds of ships we would like to differentiate, and we use as an input, for instance, the trajectory of the ship, the speed, the course, and many other features. And the output is then one of these 5 classes. But in addition, we would like to provide some explanations to the operator so that he, at the very end, has, let's say, more means to drive a decision how to deal with a specific kind of ships he can see on the screen. And it works like this. We use a special version of LIME, which is also able to deal with time series data. And this is the user interface we created to support the decision, the operator. And on the left-hand side, you can see highlighting parts of the trajectory which were driving a certain decision. So, for instance, you have to read this color coding like this. The red part of the trajectory so in this case, the ship is a cargo ship. And the red means are part of the trajectory which are against a decision of a cargo ship, and the green parts of the trajectory are parts of the trajectory which are pro the cargo decision. So now the operator gets some information on which part of the trajectory the classifier is basing its decision in this case. I now would like to hand over again to Nadia.
Okay, thank you. Okay, so let us have a look at the open challenges for XAI. We discussed a few in our papers, but there are definitely more to tackle in the future. So first of all, we need a clear definition of explainability. This is really important for also legal issues, for example, within in Europe, the general data protection, but also to be able to compare different approaches. Also, we need to maybe rethink the problem in the first place. Do we always need to train a black box? If an interpretable model is also accurate as the black box, there would be no need to take the black box. Cynthia Rudin tackles this topic pretty good in her paper that is called Stop Explaining Black Box Models for High Stakes Decisions. Another important point is the measurement of explainability. We need definitely measures to compare different approaches with each other. Also, another point would be the combination of ontologies with explanation. There is some work in this field, but definitely this should be tackled in the future more. Okay, so let me sum it up. Artificial intelligence becomes or is an increasing part of our daily lives, and the trust in AI is definitely pretty important. Explainable AI is one of the key enablers for critical domains. In this overview, we presented 5 XAI types, which lead to different types of explanations. So first, we had the model explanations. Yes. Okay, so they directly infer the black box to create global explainability. Then we have the interpretable by nature or interpretable by design, which directly is interpretable from the original model. Third, we have instance explanations, where we use the black box prediction to create local explainability. Fourth, we had the global surrogate models. Those are interpretable surrogates to create the global explainability. And last but not least, we had interpretable surrogate models to create also the local explainability. Okay, so we're at the end. Thank you very much.
Also, thank you from my side. So we are happy to answer your questions if there are any.
Well, okay, thank you, Nadia and Marco. We will appreciate the great presentation, and we'll start the part of the session. And we're going to be presenting questions that we have received in advance, as well as questions we've received from the live audience. So Rehman, I'm going to turn it over to you to ask the first batch of pre-submitted questions, and then I'll go ahead and start addressing the questions that we received live.
Thank you, Ali. So the first question is, how can we quantify the quality of explanations generated with different?
Okay. Yeah. So, well, there are some measures to evaluate the quality, but still, of course, this is pretty hard because there's not only this one measure to measure what is a good explanation. But you can, for example, take the amount of features. Are the features explainable itself? Tim Miller stated that an explanation, for example, should be contrastive, concise, selected, and social. He further also stated that they should not contain any probabilities. So there are different measures or suggestions how explanations should look like. So yeah.
Thank you. And the next question is, with different models, how can we decide which model generates accurate explanations?
Yeah, for example, you can take the model fidelity. This means like how good is the actual surrogate model is approximating the black box model's decision. So thereby you could take this as a good measure. So this would be a good first step to compare them among each other.
Thank you. And the next question is, what are the few evaluation measures that you think are good for evaluating an explainer?
I'm sorry?
I think Marco's got some background noise. Maybe you can, if you're not speaking, go on mute.
I have physically muted my mic, so it's probably not me.
Okay. No worries. Okay, so anybody who's not speaking we'll figure it out. Sorry. Go ahead, Nadia.
Yeah. Sorry, Rehman, can you repeat the question again?
All right. So the question was, what are the few evaluation measures that you think are good for evaluating an explainer?
Okay. Yeah, so also this is a good question. I mean, as I said, there's the fidelity. You can also have a look at how stable the explanations are. How comprehensible are the explanations? Like what I did before, or what we did before with the analysis with the user studies, like how comprehensible are those explanations for the users? How representative is an explanation? Like what is the coverage? All those are measures you can take to evaluate the explainer.
Yeah.
Maybe I can add a bit to this question. It's also important to consider who is the recipient of the explanation. Are you providing this explanation to a, let's say, technically skilled person who is maybe aware about machine learning models, or is it a decision maker in a company, for instance, who has no clue about machine learning? So the format and the of the explanation is also very important, and needs to be specifically be tailored to the recipient of the explanation.
Thank you. Yeah, these are the factors that we need to consider evaluating explainers. So the next question is, there are uncertainties associated with LIME because it is on perturbation, and it can also lead towards bias and variance in data set. What are your thoughts? How can we deal with it?
I mean, okay, so is the question here? I think it's the question of stability of line, right? So how can you address the stability of line?
Okay, so I think uncertainty is a big deal in many domains, not only in XAI or in LIME. So I think you need to first consider which uncertainty type you have, and then you can use it for debugging. I think this is the way you should tackle this. And also, definitely, you should try to combine explanation approaches.
Well, maybe I could add also, particularly to Lime, well, the variance of Lime also, at the very end, Lime is a linear regression model, and the variance of the model explains you a lot how about the spread of the data that is used. And the lower the variance of the Lime model, the more, let's say, trustworthy I would consider it, because then when the variance is low, it is able to fit a potentially highly non-linear black box model, at least locally, very good by a linear model. And this is indicated, for instance, by the variance of the Lime model.
Thank you. And my last question is, how can we take advantage of ontologies to improve explanations?
Mm-hmm. Yeah, well, the application of ontologies can be used to improve the data quality, but also to generate better explanations, of course. So you can include them, or you can include the domain knowledge that is improved by experts, for example, to do consistency checks before you build your model. So this could be a first good step to use ontologies to build better explanations than therefore. There are also some approaches that already take ontologies, like, for example, Trepan Reloaded. Yeah.
Thank you.
Okay, so I'll take the next batch of questions. Now, maybe I'll start with this. I'm personally curious about the toolbox. Quite interesting and novel. Could you just tell us a bit more if this toolbox is available for usage and if the code is open source?
Okay, that's a good point. So the code is currently not open source, and we will probably also not make it open source. But what we are currently doing is to provide a web service based on this toolbox, where then people can upload either their black box model or their data. They would like to have an explanation. So it works like that: you submit the data, and then you get back a prediction together with an explanation. This is currently we're working on. And this, of course, we can make available this kind of web service.
Okay, so I mean, if people are comfortable sharing their data, a web service that's freely available, and they'll get an explanation. Okay.
True.
Now, maybe some audience submitted question from the live session. And visualization can be quantified to abnormalities. Talk about or CNN, and if there are quantified metrics that you would suggest.
Unfortunately, I was not getting every part of the question. Maybe you can repeat, please.
So I think this question is explanations for a model. Are there any metrics that maybe you can identify for maybe a heat map explanation to identify anomalies?
Yeah, well, this is, I think it's going towards the same direction as one of the first questions received. Currently, there's a big lack of nice metrics that would allow, in general, the value of an explanation, particularly when it comes to these heat maps. As I mentioned in my presentation, there's often a significant amount of, let's say, interpretation still involved by the human to get the right understanding of the heat map.
Okay.
I see that it would be nice to have a nice, concise measure. We do have also having running a thesis on this currently, but currently we are not in the state to, let's say we have found the D metric or D quantification measure we need to get more information out of these heat maps and similar explanation approaches.
Okay. Thank you. Now, the next question is more trying to understand the background. Could you help explain how feature importance for random and maybe partial dependence are calculated? Maybe just give them some insight. Yeah, Nadia, maybe can you try muting if you're not speaking? Well, we don't know what the source of the. It is Nadia. Okay. Sorry. I apologize. Okay. Not a problem. Okay, so I'll repeat the question here. Could you help us understand how feature importance for random forest and maybe how partial dependence plots are calculated? Just a little bit of insight into how those answers are given. So one of you, I'm not sure who wants to answer that, Marco or Nadia?
Maybe Nadia, you can take over this question.
Sorry. You hear me?
Yeah.
All right. Okay. Yeah. So as I said previously, so the partial dependence plots illustrates the marginal effect on one or two features on the predicted outcome. Like, for example, the class Virginica. And partial dependence plots show then whether the relationship between the targets is linear or monotonic or complex. So thereby you can grasp the concept, or you can get a sense of how the classificator is judging or making its judgments. And I think the other question was regarding random forest feature importance.
Yes.
Yeah. So well, it calculates this by so the feature is important if the shuffling of its values increases the model error. So thereby, by this shuffling, you can see if the model error increases, and thereby you can get a sense of if the feature is important or not for the classificator.
Okay, excellent. Thanks for that, Nadia. And now the next question would be from the audience. The main argument against surrogate models is that there is no way to guarantee how faithful they are to the underlying model. What do you think about the future of surrogate models? Just a very broad direction into future direction of, based on the limitations of surrogate models.
Yeah, I can take over this one.
Go ahead.
Yeah, I think the question raises a good point. So the faithfulness, of course, is not fully guaranteed. This is why we were always observing the fidelity, but it's still, and I think this is the point the question is targeting into. We are not, with our approach, we are not directly, let's say, encoding the decision passes of the neural network. This is not the way how the surrogate model, at least our approach, works. But there are approaches which really try to analyze on a level of the neurons how decisions are formed, and based on this information, then a decision tree or something similar is extracted. And these one are can be probably more faithful, but this is an ongoing work in the state of art. One of these examples, for instance, is DeepRed, which is an algorithm which was developed by the TU Darmstadt, which is going in this direction.
Okay. Now, thank you for the explanation, Marco. Now, there's another question. I think this is referring to your approach that you've explained here. Is the decision tree size something that is adjusted as the model is training? In other words, each epoch, there's a new tree that is trained?
Mm-hmm. So the size of the tree is indirectly triggered. So it's not a parameter we can, it's not a hyperparameter, so to say. It is automatically generated based on the strength of the regularization parameter. The stronger the regularization kicks in, the shorter is the decision tree. This is how we can roughly phrase it. This, I think, maybe was the first part of the question. The second part is there is just one decision tree generated out of the given set of the training data. So we do not generate, let's say, multiple trees. We are currently investigating an approach that we get some localized decision tree to get a more, let's say, locally accurate decision tree, and based on it then form a larger one. This is ongoing work. Maybe this answers part of the question, but in the current implementation, so what you have seen in the demonstration, we only generate a single one, and this is depending on the given set of training data.
Okay, excellent. Now, thanks for the explanation, Mark. Now, the other question here is, what are your thoughts on choosing the right explainer for the particular classifier and data set? For example, Lime assumes local linearity, and if that condition is not satisfied, it may not do a good job over there. So are there any thoughts into assessing the fit of the explainer to the particular model and data?
Yeah, that's a good question. And currently we are preparing something which we can call a cheat sheet. So a decision diagram which is allowing the user, based on various information of the problem, like which kind of data, for instance, which kind of problem setup, and so on and so forth, to get a decision support, which kind of explanation should be used. Probably we will release this in March, February or March of this year, so quite soon.
Actually, I'm glad that you're doing some work in that area. That's one of the main areas for confusion for the practitioner community, and there's a concern about the explanations that we're getting are being misleading. So it's a very important contribution that we're looking forward to. Now, which I guess leads me to the next question is, could explanations sometimes be misleading, or lead users to develop a false sense of confidence in a machine learning system?
Nadia, maybe you want to answer this question?
Yes. Yes, definitely yes. If you have bias in your data, I mean, the explanation only shows what you have learned in the data, okay? So if there's already a bias within the training, of course, you will have the model that is biased, and also you will have the explanation that is biased, and also, sure, the user will get a wrong idea of this.
Yeah, so maybe there's a follow-up question on that. So would it be fair to say that explanation methods are getting good at, or are good at identifying bias in our models, but they're not the absence of bias?
Yeah, well, I think, explanations are pretty good at detecting bias in the first place. So definitely that's a yes also.
Okay. Now, maybe there's another question here is, could you help us understand the difference between kernel SHAP and linear SHAP? What just do a bit of a comparison between those two explanatory methods?
Yes. So kernel SHAP is a model agnostic method to approximate the SHAP values using the idea of Lime and the Shapley values. And linear SHAP is really for specific models, so for linear models. So if you have a linear model, you are better with to take linear SHAP. instead of taking kernel shap, because I think it will be more accurate because it uses the specific parameters.
So from a decision guide, when you have a model-specific explanation, like tree shaft for models or linear shaft for linear models,
Yeah.
that rather than kernel shaft.
Yeah, that's true. For instance, there's also, I think you mentioned it, there's also tree shap, which is dedicating for random forest models. So it's especially optimized for speed. Maybe you all know that calculating Shapley value is quite expensive computationally wise. And if you do have a random forest model, tree shap is significantly faster than the, let's say, general purpose kernel shap.
Okay, beautiful. And maybe this is the last question we have. Have multiple. I mean, and I think it's really upcoming line of work. If you have multiple, and you're getting different contradicting explanations, what is your recommendation, or which explanation to use? I mean, it's a very broad question. We can make a very general statement and look for your upcoming work for a guide.
Marco, would you like to go first, or?
Yes, I think part of it we answered already with the cheat sheet we're currently working on. There's no general answer to this. Maybe there will never be one. It has multifacets to answer this question. One is this cheat sheet we're working on, but I think also very important. This is what Nadia raised with the one slide, that we should rethink often how we tackle the problem. Like always shooting with a deep neural network on a problem is not a good idea. If we can solve it with a significantly simpler explainable model, we should do so. But it's somehow often forgotten. I also see it in practical works. We are doing many projects with companies, and these guys are often then directly coming, oh, let's use a neural network. And I ask, is it really necessary? I prefer always to start simple. Start with the simplest model. You can think about the problem and also the experience you do have. And if it's not sufficient, then think about if you need something more sophisticated. So really start small and simple, and the simple models are often also the explainable ones.
Okay. Well, and that's a really good maybe last question to end on, and I think that's a very sage advice. Now, before we wrap up, are there any final thoughts that you'd like to share with us? And if not,
Yes.
I think Marco's answer was a good closing statement, if that's okay. So Nadia, Marco, I congratulate you on a significant contribution to the field, and thank you for a great presentation. We also look forward to your future work, and we thank all of you who joined us online and submitted questions in advance. To see more content like this, please visit our website at ai.science and log in to access slides from this and other sessions. Also, make sure to subscribe to our YouTube channel, ML Papers Explained, to get notified about all the live sessions and free content we publish. This concludes our event. Thank you for watching.
Thank you as well.
Thank you. Bye.